shift our attention to the idea of what's called continuity with piecewise functions. Continuity is an idea of continuousness. In other words, the graph of the piecewise function has no holes or jumps. Has no holes or jumps. When I speak of a hole, what I mean is if the graph looked like this, it would be going along, it's a missing value, and it keeps going. And when I speak of a jump, what I mean is the value is going along, jumps up to another one, and keeps going. A good test for continuity is, can I draw the entire function without lifting up my pencil? If so, we're going to call it continuous. We'll have a more formal definition of continuity later, but for right now, I want to look at this in terms of piecewise, just to see if they're continuous. So for example 4 and B, we want to see, are the piecewise functions continuous? Do they keep going? Now, when I look at piecewise functions, I only have to look for continuity at the transition points. I need to check the transition points. So really, I'm asking myself the following question. Does the closed dot fill in the open dot? That's what I'm asking myself. Because if they fill each other in, it's going to be continuous. If they don't, I'm going to have one of these two situations, either a jump or some sort of hole. So that's what I'm going to check each time. So for examples A and B, I want to go through, we're going to determine it algebraically first, and then we're going to graph to confirm what we think. So for the first one, my transition point is at 2. You can see that right here from my x value. So what I'm going to do is I'm going to go through and say, okay, the closed dot and the open dot. Closed dot comes from that guy down there. It's going to be at 2 comma, plug in 2, and I get negative 6 plus 4, or negative 2. 2 negative 2. I'm just taking him and plugging him in to what the function is. The open dot, put a little close open there, that might help. The open dot is going to come from the top guy. Take that 2, plug him into there, and you're going to end up getting out a negative 2. So if you can see here, the closed dot and the open dot are the same. The closed dot fills in the open dot. So I'm going to say that this is continuous. C-O-N-T-I-N-U-O-U-S, continuous. Now let's confirm it with the graph. Let me scroll down just a little bit. Keep scrolling back up on me. If I graph these like I normally do, I'm going to call him blue, and I'm going to call him red. I'm going to say, okay, 2 comma something is my open dot, and I found out that that's negative 2. So I go to 2 negative 2, put my open dot. Notice his channel is below 2, so his channel is on that side. So I pick an x value on that side. I'm going to pick the x value of 1, plug that in, and get negative 3. So he's just giving me a good representation of what the graph looks like. For the red one, we already saw, well, 2 comma something is a closed dot. We saw that that's negative 2. So he fills in right there. That's going to make this a continuous function. Now his channel is above 2. So I'm going to pick an x value above 2, 3. And I'm going to plug that in and get negative 9 plus 4, which is negative 5. So he's going to go the whole way down there, almost off my screen. And he's going to go down. So the key is, as my graph is coming along from left to right, purple here, I can draw this entire graph without lifting my pencil. That's what's going to make this a continuous function. Looking at example B, I want to look at closed dot and open dot. The closed dot is going to come from this guy down here, because he's greater than or equal to. The open dot is going to come from that guy up there, And I want to see, do they fill each other in? So the closed dot is 1 comma, and if we remember, these give me the y's over there, 1 comma 5. It's always 5, no matter what the x is. The open dot is going to be 1 comma, whatever negative 2 times 1 squared plus 4 is. That's going to give me 1 comma 2. So I'm starting to think that the closed dot does not fill in the open dot, hence this is not continuous. I'm going to have to lift my pencil as I'm drawing this function at some point. So if I look at graphing this, to confirm, I'm going to start with the red. I know that he's at 1 comma 5 with a closed dot. If I go to 1, 5, the closed dot. Now some people are a little confused. They're like, well, how do I get other points? Follow the same process. I know he lives in that channel above 1, so pick an x value, such as 2, plug that in, and you're going to notice that the output is always 5. So it's 2, 5, so I have a horizontal line going that way. With the quadratic, they're a little trickier to graph. I always start with the vertex of a quadratic. And in this case, it hasn't been moved left, right, but it's been moved up 4. So I go to 0, 4, and I put my dot. Now, you can go ahead and plug in 1 if you want to see what it is. If I put in the number 1, we already saw that it gives me a positive 2, and it's an open dot. That's all right there. 1 comma 2 is an open dot. So I go to 1, 2 with an open. Depending on what you know about quadratics and graphing them, you can reflect and get an actual point right there, or you could plug in negative 1 and you'll also get a 2 out, whatever you need in order to get your graph. Notice he keeps going on the left because my channel here is everything down there. So I'm going to put an arrow on his left, but as I come to the right, my graph's going to end. So there's my function, and we're going to say he's not continuous because if I try to graph him without lifting my pencil, I can't. I end up down there, and then I've got to lift it and go that way. So he's not a continuous function. We're checking, does the closed dot equal the open dot? Last concept for piecewise here is example 6. We need to go through and actually write the piecewise function. So whenever I go through to write them, I identify all of my sections first. So I've got one section there, second section there, and a third section there of my graph. So I'm going to go ahead and set up my big bracket. I'm going to say, here are my 3 functions, and then each of them carries with it a channel. So if I look at the channel for the first one, it's from that x value to that x value. So that would be from negative 5, and if you look and I uncover it here, you're going to see that at the negative 5, I have a closed dot, and the whole way up to 0. So I'm going to go from negative 5 up to 0, and I'll put the x in the middle. And if you're writing this, they always point to the left. So negative 5 is less than or equal to x. And I'm going to say that x is less than or equal to 0 because there's not a missing point there. Now we'll talk in a second about some options I have, but that's going to be my first section right there from negative 5 to 0. You can see that the second section is going to go from 0 up to 3. So from 0 up to 3. And at 3, he's a closed dot, so I know he's less than or equal to. Now at 0, since I already made one of these equal to up here, I already have a closed dot there, I want to keep it a function, and I want to make sure that I just put a less than there with no equal to. Now I could have switched these two things and made this one up here strictly less than and the one down below less than or equal to. It doesn't matter as long as you don't double up. That'll be okay. And if I look at my third section right here goes from 3 to 6. So from 3 to 6. And I can see that he's open on that side, so he's just less than, and he's closed at the 6, so he is less than or equal to. So I'm going to go ahead and get my graph cleared off so I can actually write these equations. It's really important to realize what kind of function you're dealing with. The first one, from here up to there, that guy is linear. So to write a linear, I need m and I need b. To find m, you have to find the slope. So this guy goes up 1 over 2. So he has a slope of 1/2. And to find b, we need to find where does he hit the y-axis, and he hits the y-axis right there at 2. So when I go to write my function, it's going to be 1/2 x plus 2. And he's living in that red channel that we already determined. For the second one, going from here to here, we've noticed already that if I have a horizontal line, I just go with whatever the y value is. So he's just going to be 2, because the function is always 2 from 0 to 3. And for the last part, again, I have a linear, so I need m, I need b. M looks like it goes down 1 over 1, so negative 1, 1. So my m is just negative 1. And for the b, you could use point slope form or slope intercept, any of that, or you could just trace him back and see if I go up 1 over 1, up 1 over 1, up 1 over 1. You can trace him back to see that he's going to hit at 4. So if you can count on the graph, that's wonderful. That saves us a little bit of the algebra, and it gets us the y-intercept pretty easily. I just counted and continued the pattern. So this is going to be negative x plus 4. So there's my function, and up here it said that my function's name is x. I just constructed my function from all the different pieces of the piecewise.